In example 5 and 6, we want to apply this idea of linear programming again. For example 5, we have an investment broker who's instructed to invest up to $23,000 in a junk bond yielding 9% and in treasury bills yielding 7%. Client wants to invest at least $8,000 in treasury bills and no more than $15,000 in the junk bond. How much should they recommend that the client place in each investment to maximize income? So in this case, this idea of optimizing becomes a maximization problem. If the client insists that the amount invested in treasury bills must not exceed the amount placed in junk bonds. So what we have is a case where some amount of money will be invested in an account yielding 9% interest, and some amount will be invested in an account yielding 7% interest. We want to maximize that value so that we're getting the best return on that investment. Some of the things that we know is that we're going to be investing up to $23,000. So x plus y has to be less than or equal to $23,000. They want to invest at least $8,000 in treasury bills. So y, the amount invested in those treasury bills, has to exceed $8,000 or be at least $8,000. And no more than $15,000 in the junk bond. So our value for x has to be less than or equal to $15,000. And in the last sentence, we're told that the amount invested in treasury bills must not exceed the amount placed in the junk bonds, which would mean that y has to be less than or equal to x. We again have a couple of implicit statements, which would be that x has to be greater than or equal to 0, and y has to be greater than or equal to 0, because we can't invest negative money. So we'll turn to Desmos to enter each of these as an equation. And then entering any of our inequalities first, with the remaining inequalities as restrictions. We can adjust our window to visualize our solution, which took a little bit more scrolling in this case since we're dealing with some larger values. But we see our bounded region with each of our corner points, 8,000, 8,000, 11,500, 11,500, and 15,000, 8,000. In order to maximize our investment, we can again construct that table, and in a new column, we'll type in 0.09x1 plus 0.07y1, and then enter in each of our different pairs of values. So we have 11,500 and 11,500, 8,000 and 8,000, and 15,000 and 8,000. So what we can see is that we get the largest return on our investment, that 1,910, when we invest $15,000 in the junk bonds and $8,000 in treasury bills. So that maximum return of $1,910 is going to come from investing $15,000 in junk bonds and $8,000 in Treasury bills or T-bills. I'll let you read through example 6 on your own, but what you should be able to determine from this is that we'll want to look at maximizing 9x plus 13y with the restraints that 6x plus 4y should be less than or equal to 144. 1x, or just x plus 3y, should be less than or equal to 66. And we again have those implicit restrictions that x must be greater than or equal to 0 and y must be greater than or equal to 0. So clearing everything out that we had just typed in, we can graph these new equations. As well as the inequality statements. And then zoom in to see what our bounded region looks like. Again, we have a few corner points here, which we'll plug into a table of values to determine where we get that maximum value. In this case, looking to maximize 9 times x plus 13 times y, we can use x equals 0, y equals 22, 12 and 18, 24 and 0, and our last pair would be at 0, 0. We can see that we're going to get a maximum profit of 342. So we get a maximum profit of $342 by producing 12 racing skates and 18 figure skates.